When you build a projection for W, the first step will be to find a basis, and not any basis for W. You'll need a special basis, and that's what we need to define next. So if I take a set, so let's say V is an inner product space. And I'm going to take any subset. I'm going to call S orthogonal if all the elements are S are perpendicular. I'm going to call it orthonormal if they're perpendicular and each of them is a unit vector. So first, S is orthogonal if I take two elements of S, any two elements, as long as they're not the same, then VW is 0. Alright, so that means the angle between them as defined by this inner product is 90 degrees. So they're orthogonal, they're perpendicular. And then BS is orthonormal if they're orthogonal so that means all the vectors are perpendicular. And second, any V in S has a length of V equal to 1. Right, so that's even more special, and we're going to call those set orthonormal. Alright, let's try an example. So I'm going to look at V in R3. The Euclidean space, that means I'm taking the standard product, the dot product that we had before, with a usual dot product. And I'm going to look at S is 1, 1, 0, 1, minus 1, 0, and 0, 0, 3. Alright, first question is I want to show that this is orthogonal. Right, so I have three vectors. I need to show that any pair is orthogonal. So let's take these two. I'll compute their inner product. Again, because this is Euclidean space, I'm using the dot product. So I'm going to get 1 minus 1, which is 0. That's perfect. So these two are orthogonal. Let's compare these two. That's 0 as well. And finally, done these two and these two. I need the last two. So that's 1 minus 1, 0. Dot 0, 0, 3. That's 0 as well. Alright, so since I got 3 zeros, that means S is orthogonal. Alright, so it's a nice basis for R3. Alright, then I want to show it is an orthonormal. Alright, so I know it's orthogonal, so the only problem will be the length. Some of these vectors might not be normal. So let's try the first one. I'm going to look at the length of 1, 1, 0. That's equal to square root of 1 squared plus 1 squared. That's square root of 2, which isn't 1. So S isn't. It isn't orthonormal. But I claim that from this S, we can get a set that's orthonormal. All I have to do is shrink or stretch the vectors, keep them in the same direction, but shrink or stretch them so that their lengths are 1. So let's do that. Right, so let me draw the picture of what's going on. Right, so I have R3, I have X, Y, and Z. The last vector is the easiest to sketch, so let's start with that. We have a vector here, 0, 0, 3 of length 3. Then I have 1, 1, which would be here. And we have 1, minus 1, which would be somewhere here, and you have a right angle here. Alright, so they are orthogonal. Now I want to stretch them, or shrink them in this case. So I want to take a vector in the same direction, but of length 1. So the first vector was this one. Let's shrink it appropriately. So I'm going to take V1 to be, well, this has length root of 2. So I'm going to shrink it by dividing it by its length. So I'll get 1 over root 2, 1 over root 2, and 0. So it's parallel to what I started with, but now it has length 1. Alright, let's do the second one in a similar way. V2 is 1 over its length. 1 minus 1, 0. Of 1 minus 1, 0. And so I'm going to get again 1 over root 2 minus 1 over root 2, 0. These vectors are unit vectors, and they're still perpendicular because they're in the same direction as the one we took before. And finally, V3, I'm going to take 0, 0, 3 and divide it by its length. And so the length is 3, so I get 1/3 of 0, 0, 3, which is 0, 0, 1. Right, so the new set, which I'll call T, is going to be 1 over root 2, 1 over root 2, 0. 1 over root 2 minus 1 over root 2, 0. And 0, 0, 1. And this is orthonormal. Alright, so these vectors all have length 1, and they're all perpendicular pairwise.